Welcome to another unit in business mathematics. This time I'm going to talk about integration, and here in particular on the so-called rule for partial integration. Let's have a look at the exercises. Here we have calculate the following indefinite integrals, and then we have these three examples. First off, x times exponential function of x, then x times sinus of 2x, and finally x squared times ln of x. Well, let's work our way through these three examples step by step. And we start with x times exponential function of x. Whenever we see that actually we have to calculate the integral of an expression which is more or less the product of two expressions, one question we can ask ourselves, is one of the two parts becoming simpler when we derive it, and is the other part not becoming significantly harder when we actually get its primitive? So if we take a look here, what we can see is that the x can easily be derived, giving us 1. On the other hand, the exponential function can easily be either derived or we can calculate its primitive, because in either case remains the exponential function. So if we know this, we can set as function u the first part, the x, and the u is what we will derive. So here we take the derivative of u, which is 1, and then the other part, the exponential function, we call the derivative of v. That's the second part here. That's actually the derivative, and now we need the primitive of this. So we need to integrate it, giving us here again exponential function. Once we decided and done this, we can actually use the rule for partial integration, which simply states that this integral becomes two parts. First off, here we take the u and the v, multiply these two, so the two normal functions, giving us x times exponential function of x plus a c as some kind of constant. And then for the second part, so this simplified integral, what we do is we now take these two parts. So the original one have those two. Here we now take these two, multiply them, so giving us here 1 times exponential function of x. Well, this simplified the expression because now we only have to integrate exponential function of x, and well, as we said before, this remains the same. So this results then first this part here, x times exponential function of x, then minus, that's from the rule for partial integration, and then here integrating exponential function of x, giving us the exponential function again, and plus c. Well, we could then continue and here factor out the exponential function of x. That would look like this: x minus 1 times exponential function of x plus a c. Okay, so that's already everything there is to the first part of this exercise. So let's have a look at the second part, part b. This function here looks pretty similar to what we had before. Here we have x times sinus 2x. Well, it actually is because we proceed in a similar fashion. We know x can easily be derived. Well, sinus 2x, that's not so easy to be integrated, but the important thing is that if we combine the two parts after derivation and integration again, the expression as such needs to be simpler. So if x becomes 1, this usually means this will be the right way to go. Except if the other function is making this way more complicated. Here, we know sinus and cosinus always switch, so it's not this hard regarding the integration of sinus to x. Well, let's first state, however, the function we want to derive, that's x. Derivative here is 1. The function where we need the primitive, that's sinus to x. Well, with sinus to x, from sinus or to sinus, we get from the cosinus. However, the cosinus derived is minus sinus, so I have to put a minus here as well. Okay, this takes care of the sinus, but we have 2x, so we need to have 2x here as well. If, however, we were to derive minus cosinus of 2x, we would get a 2 here. So to get rid of this, we multiply this with 1/2 as well. If this is too complicated to understand, why we select here this v as is, calculate the v as is, you could in this step go even more detailed and apply the substitution rule in this regard as well. So if you use the substitution rule on sinus 2x, this will actually yield you minus 1/2 cosinus 2x. Okay, once we have this, let's put this together with the rule of partial integration. So first off, u and v, so multiplying these two, giving me minus 1/2 x cosinus 2x. So that's the two parts here. I only move the x in between there because this is more like mathematical notation. And then finally plus a constant c. Okay, that's the first part. Then the second part, we get minus. Now we need those two. So here we have 1 times minus 1/2 cosinus 2x. Well, the minus and the 1/2 we can drag in front of the integral, making it look like this. And then we only have to take here the integral of cosinus 2x. Well, that's similar to what we did up here with the sinus. The only difference, I get to the cosinus from the sinus. And well, in this case, I actually do not need a minus in this context. So here I will actually can keep it as it is regarding the sign. However, I will again get a 1/2. Similarly as with this case, if you want to get into more details, you might also use the substitution rule here. However, well, I would get a new 1/2 in front of the cosinus or the sinus 2x, making it look like this. So from the first part, I have minus 1/2 x cosinus 2x. And then from the second part, I have plus. Then I had 1/2 from before times another 1/2, making 1/4 sinus 2x. And then finally plus c. Okay, so this, well, we cannot simplify this anymore, so this takes care of this exercise part B. Let's then turn to the third and final part. Here, we actually had the integral over x squared ln of x dx. The first intuition in this context, especially regarding my earlier comments, might be to go with, well, I can simplify this if I just derive x squared. Well, that's right. This will look simpler. However, the problem with this is the primitive of the logarithm does not really become easier. It becomes even more complicated. So in this regard, going for deriving x squared and integrating ln von x. That's not the nicest way to go. You could try this. In the end, you might find a way to work this way as well. However, this will not be the easiest way to go. Much easier will be if we take the derivative of the ln, because the derivative of the ln is 1 divided by x. So this will actually simplify even if we integrate this part here. So mentioning this, we select as u ln of x, making it simpler in regards to the other function, where we then get as a derivative 1 by x. And as the derivative of v, we take x squared. And here the primitive is 1/3 x to the power of 3. If we then plug this together, first off, u times v, giving us 1/3 x to the power of 3 ln x. So those two, plus c, minus then the integral of those two. So 1/3 x to the power of 3 times 1 divided by x. And here we can directly see the x to the power of 3 and the 1 divided by x. They can be summarized into x squared. So here I get x squared, and the 1/3 I can pull in front of the logarithm, the integral, making it look like this. And well, actually pretty easy and pretty straightforward to get the primitive of x squared. Basically we have this up here already. So I can just put this result instead of this integral here, giving me this final solution. So it's 1/3 times another 1/3, which is in front of the integral. That's here the 1/9 x to the power of 3 plus c. Then I could continue and, for example, factor out the x to the power of 3 as well. However, at this point we can already stop, because this took care of everything which is important in this regard. So in some cases, having a polynomial expression here might be misleading if the other function is actually making the situation harder if we derive it. Especially this is true in most cases for the logarithm. And well, that's already the third and last part of this exercise. So I hope you enjoyed listening to it. And well, so far I say goodbye and see you next time.